It's a great pleasure to be here. I love Encinitas. I love meditating on the beach here. And I want to thank Stuart for inviting me, and Stuart for his long dedication, and both Stuart and Roger for their deep inspiration to make this word consciousness a part of the scientific dialogue. They have really been campaigning on that for many years, and we really owe them for this conversation today, and I think what will become one of the most defining questions in physics and medicine and science in the decades to come. So thank you very much. Okay, so it's a pleasure to be here today, and amidst the hurricane that's happening outside and the one that I guess we're causing inside. So I'm going to talk to you about nanomachines that read and write DNA and the prospects of how they may be processing information, classically and quantum mechanically, and examine this question of consciousness, especially in the context of living systems. I run a research institute in Cambridge, Massachusetts, and a spin-off company called Nanobiosym. And our institute and incubator focuses on creating science and innovations at the nexus of physics, biomedicine, and nanotechnology, information communication technology. And part of this interface, we look at how do we look at the physics of life, living systems, and consciousness, and use some of these tools and technologies to really address that question. What you see here is a nice landscape in rural Mississippi where I grew up. Can you hear me okay?
Yeah, we're just getting flickering on you.
Oh, okay. And I used to spend a lot of time meditating in this kind of landscape in Mississippi, and at a young age, I learned to live at the quantum superposition of many worlds that didn't talk to each other. My parents had emigrated from India to rural Mississippi, and I grew up going to a Southern Baptist church for school where black and white people lived on different sides of the railroad. And my dad is a surgeon, so I used to get to go to the hospital with him while he's doing surgeries and make rounds. And I love physics and mathematics. And at the home, in our home, we were exposed to concepts of Eastern philosophy like Vedanta, and at school, Southern Baptism and the Bible, and I love science. So you can see kind of a quantum superposition of many different worlds that didn't talk to each other. And I became convinced that there's got to be an underlying unity in all these fields of science that we are pursuing. And I really became fascinated with physics and medicine. And the deeper I went into the study of those, first at Stanford, then Harvard and MIT, the more aware I became just how deep this divide is between these fields in our current modern framework. Most of our physics today is the physics of inanimate matter that hasn't come to terms with life, living systems, and consciousness. Our 20th century physics was developed in the context of systems that operate close to or near equilibrium or at equilibrium, where an interaction with their environment is at best a perturbation. And living systems are fundamentally open systems. They exchange matter, energy, and information constantly with their environment. And most of our medicine is practiced at the level of chemistry and molecular biology, hadn't really come to terms with things like how physical forces, mechanical forces, electromagnetic fields, quantum effects can play a role in physiological systems. So I was pleased to see that Einstein, towards the end of his life, came to a similar conclusion, that one can best appreciate from a study of living things how primitive physics still is. So 100 years ago, Albert Einstein gave us a framework to understand matter and energy on some kind of equivalent footing, popularly known as E equals mc squared. Are we getting a flickering still? Let me see if we can fix this. this good? I believe that in order for us to use the mathematical machinery of physics to come to terms with life in living systems, we have to expand this framework. And we have to expand this framework to include things like information and consciousness. And we need to be able to understand the interplay of how matter, energy, and information, and even consciousness talk to each other and interact with each other. And we have to make that a hardcore physics problem, not relegated to metaphysics. And as we know, when quantum mechanics came about, Einstein felt that something in quantum mechanics was missing. There's some part of reality that's not being described by the quantum mechanical description. And it wasn't just Einstein, de Broglie, Schrödinger, Dirac. They all started to believe that there's something missing in quantum mechanics that doesn't describe the full picture of reality. So one of the thoughts is that if we apply quantum mechanics in living systems and we start to look for non-trivial quantum effects in life in living systems, will we learn something about what's that little missing factor potentially in quantum mechanics? And so I'll talk a little bit about that as well. And if so, can we start to understand what are the components, or how do we go about trying to understand how matter, energy, and information interact with each other? And I think this is going to take not only work in theoretical physics, but also we need experimental laboratories and tools to begin to examine this question. So that leads me to this. These are tiny nanomachines whose job in life is to Xerox DNA. And I fell in love with these things because for many reasons. One is I feel like they're a good experimental laboratory to understand the interplay of matter, energy, and information at the nanoscale. Because these little nanomotors, they crawl along the DNA and they convert single-stranded DNA to double-stranded DNA, a process known as DNA replication. And there are tools that have become available from quantum optics and nanotechnology that make it possible for us to take a single molecule of DNA, this entire process in real time, and begin to ask questions about how information embedded in the environment might talk to or modulate how this nanomachine reads and writes DNA. So I hypothesized some years ago that your DNA is like a piano, and the music that you as an organism make is an interplay of the information encoded in your DNA sequence, the information encoded in the environment, as well as, if I may be so venturesome to say, is
Swap mic. Battery went down.
okay, we have all kinds of tissues. All issues happen. Okay. So this interplay of the information embedded in the DNA sequence, the information in the environment, and the information in, let's call it for the moment, consciousness, whether it's your consciousness or a generalized consciousness, we'll revisit that later. That interplay actually modulates what information gets manifested out of that DNA. Let me say it a different way. DNA is an information storage molecule that stores information on many scales. And how you read that information actually affects what information you get out of that information storage device. And these nanomachines are the read-write machines of nature that write information into this code and retrieve information out of this code. So one of the hypotheses is, could evolution, at least at the molecular level, be somewhat more Lamarckian than Darwinian? Instead of being purely random, could influences from this molecular environment be modulating how evolution occurs, how the flow of genetic information occurs? Another aspect of this is, could information in the environment be modulating which genes get turned on, which genes get turned off. Now we know that from epigenetics, but could it be other kinds of information? Could it be physical forces, like mechanical forces, electromagnetic fields? Could other kinds of information be communicating with how these systems are reading and writing information into DNA? So you can see this kind of fascinated me on many levels, but also it's a laboratory to begin to study this interplay of a system that's fundamentally open, that's exchanging matter, energy, and information with its environment. So I'll come back to the network. So I kind of launched into this on many levels, both from a theoretical side, and my lab at Nanobiosym began harnessing some of these tools to build tools to precision control these nanomachines that read and write DNA. And several of these agencies started funding us more for the commercial and the applications that came out of this than some of the deep science that actually inspired me for this. But these are some of the applications that come out of being able to precision control nanomachines that read and write DNA at the single molecule level, including new ways of sequencing and amplifying DNA with high resolution. But also something I'll talk a little bit about is, can this be a machinery for information processing, information storage, and even quantum information processing? This example of a commercial product that our commercial spin-off company is built, being inspired by some of these precision control capabilities. So here's just some of this is more of a classical control. Here we can take the mechanical stress on a DNA molecule, the tension in piconewtons, and by tuning it, we can control the speed and the direction of how this little nano machine reads and writes DNA. One of the editors of Scientific American got excited by this, and so we got this little cover art inspired by oops, you guys have some issues. You able to see this?
I'll take this adapter from you.
What are you trying to do?
I'm going to switch this adapter out.
Well, why don't you,
For a new
oh, you got another one, okay.
Thanks.
This is the most, all right. Feel free to ask questions to, are we getting? Are we playing? So this is an example of some of the things we can do in our lab. We can stretch out single molecules of DNA and visualize in real time as a nanomachine reads a DNA code. And we can measure the position versus time. And notice as we change the mechanical tension, tuning a DNA string, we can slow down the rate at which the nanomachine reads the DNA. Here we're slowing down the replication process. And if we put just the right amount of tension, we can make the DNA motor stop dead in its track and stop replicating DNA. And then if you put even more tension, you can induce the motor to reverse gears and start running backwards and unzipping the DNA. Now this is an example of how mechanical forces, no chemistry, no biological system, but can modulate how the information encoded in DNA is being expressed. And that, I believe, is the tip of the iceberg of what else could there be in the environment that can modulate. And so we've not only done the experimental kind of methods to measure this, there's some measurements we've made on how tension changes the speed at which the motor is running along the DNA. But we've also been building we have published a number of papers on the theoretical framework to describe this experimental data. I won't have time to talk about all that, but here's how, for example, we can record the motor being tuned as it's copying the DNA or as it's editing the DNA. It's proofreading the DNA. So now I'm going to move into the next phase, which is how can we not only precision control these motors, but can we quantum control these motors? And here's a chapter I did in a book, actually, with a foreword by Roger Penrose, looking at, are there quantum mechanical effects in biological systems that are non-trivial? And I examined that in the context of our nanomachines. So can these nanomachines process information quantum mechanically? And if so, could nature have already built some of the first quantum computing systems in the context of living systems? So why is it important to quantum control these nanomachines, and why is it important if that does happen? Well, if quantum mechanics plays a non-trivial role in the physics of life and living systems and this thing called consciousness, then that would help us build a more complete theory of everything and help perhaps resolve some of those 100-year-old questions about what's missing in the quantum mechanical description of reality. And there are also practical applications in terms of information storage, quantum computing architecture, understanding the role of quantum mechanics and molecular evolution. I won't have time to get into all these, but just giving you kind of a flavor. Now, I didn't talk about some of the theoretical work we did in understanding, does this laser point away? How this nanomachine moves up and down DNA and how knobs from the environment can couple into and control its translocation. So I modeled this I spent a sabbatical at the Santa Fe Institute thinking about biological networks and modeled this nanomachine as this algorithmic state machine going through a series of internal states, and modeled how knobs in the environment could couple to and modulate this movement along the DNA. As part of getting a language to describe a strong coupling between the environment and these nano systems. And I'm just going to show you one dimension of this, which is, first of all, these are the 5 requirements for a system to be a quantum computer. And we analyze how this DNA nanomotor system could be a quantum computer. If it meets these 5 criteria, we can argue that a system can be a quantum computational system. So I'm going to go through this a little quickly, but I'm going to spend a little bit time on showing you how we argued how the decoherence times of this DNA motor system are such that they're much longer than the gate operation times, or the information processing time, the time it takes for the nanomachine to read one base on the DNA code. So first of all, these systems have, I argue, well-characterized qubits that can be measured, operated on, and initialized, some of the 5 criteria. You can define the state vector of this nanomotor as psi motor to the nth as a quantum superposition of these internal states, these 5 states. When it completes one cycle on these states, the DNA grows from n to n+1. And you can define a set of unitary operations that operate on these states. One of the other requirements for a quantum computing system. So I'm going to kind of go through this a little quickly, but if in that paper I calculated the decoherence time, or estimated the decoherence time of this nanomachine DNA system, and use some of the polymer relaxation times to get there, and then that gives you some range of what that so bottom line is the decoherence time can be on the order of minutes to hours, and the key base pair reading time is on 10 milliseconds. So you clearly satisfy the requirement of having non-trivial quantum mechanical phenomena operate in these systems, where the time scale of maintaining coherence is much longer than the time it takes to read one base. So one of Roger Penrose's colleagues, John Barrow, actually applied Wigner inequalities that he calculated for how to put constraints on the measurement of space-time in a quantum clock. He applied that to a black hole to calculate the accuracy and the precision using these Wigner clock inequalities. And it turns out that the maximum running time of a quantum clock can be estimated by the mass, a length scale, and Planck's constant. And if you apply that to a black hole as a quantum clock, you get the Hawking lifetime of a black hole and the short cell radius of a black hole. Likewise, the precision of a quantum clock is the minimum time it can register. You can apply that to a black hole and you get the fastest information processing frequency. So we apply that to our nanomotor system, and lo and behold, we get a time scale for the maximum running time of this motor on DNA of about 380 seconds that it can run and still be accurate. It's like one of those grandfather clocks. How long can they run before they lose their accuracy? And that corresponds to Taq DNA polymerase, which, you know, on the order of magnitude makes an error every 100 seconds. And the precision of this nanomachine is the minimum time it can register and still be accurate. And that, if you plug in these numbers, corresponds to about 10 to the minus 15 seconds, a femtosecond, which is about the lifetime of these internal states, as known from quantum chemistry. So now if you plug that in and you calculate the information processing power of one of these little DNA nanomachines, you find out that, I'll just cut to the chase, this nanomotor is making 10 to the 11th computational steps for every base pair that it's reading. That's a lot of computation that this little nanomachine is doing to read one base pair. So the question is, why so much decision making is required in its choosing its movement to those internal states and its translocation along the DNA? Could it be that there's just, because it's reading the DNA sequence, or could it be that there's other information in the environment that's modulating and talking to it that it has to decide between? And so there's a lot of information processing going on at a very high information processing power at this system. So now I'm going to be a little venturesome in the theme of this conference and talk about stretching this a little bit. Just like information embedded in the external environment is inherently, we argue, coupled to how the nanomachine is reading DNA and choosing between some of its states, could it be that consciousness or the mind is also inherently coupled to these systems and helping them choose between their internal quantum states? For example, what we currently call chance or randomness, could that, and I'm venturing to say, that the missing ingredient is consciousness as part of that underlying fabric of reality that's helping to decide between quantum states. I know I said a lot there. Here's another way of saying it. Actually, Freeman Dyson said this some years ago. I think our consciousness is not a passive epiphenomena carried along by chemical events in our brains, but as an active agent forcing the molecular complexes to make choices between one quantum state and another. In other words, mind is already inherent in every electron, and the process of human consciousnesses differ only in degree, but not in kind, from the process of choice between quantum states, which we call chance when they're made by electrons. Now, this is another angle that's starting to define what's the intelligence of an organism, an artificial machine, or an information processing device. Here I estimate that by the information extracted by the machine or the organism from its environment on top, and on bottom is the information contained in the environment. So a more intelligent organism gets a higher ratio of the information in its environment it's able to extract. Now the question is, what is this information in the environment? And could it be a hierarchy of information, not just in the environment, but also what we might call a more generalized consciousness? I'd like to have some questions because I know I said a lot of things and covered a lot in this time. And, but I will leave you with a thought. At the sabbatical I spent with, at the Santa Fe Institute, I used to spend a lot of time with Murray Gell-Mann, talking to him over lunch, and he agreed when I said the prevailing scientific paradigm, he agreed with this definition, is that life, mind, and consciousness are emergent phenomena that emerge when matter attains some critical degree of complexity. Then it starts to manifest self-awareness and consciousness. I believe that as we advance some of these new capabilities and ways of thinking, that we might find that the laws of physics are consistent with and provide new insights when we look at a new and perhaps ancient scientific paradigm where information, consciousness, and mind are something fundamental to the fabric of reality, even more fundamental than matter, energy, and space-time. And matter, energy, and space-time emerge from that underlying reality. So I'd love to ask questions. I know I covered a lot of grounds, so the best is, I'd love to do some Q&A.
Thank you. Let's give a round of applause.
Gina, yes.
Kind of definition of looking at information within the environment and, you know, comparing things with chance and everything. But from a lived experience, wouldn't that be considered presence? You know, just being very present to the moment? Because when you're present to the moment, your bandwidth of information coming in is a lot more than arguably when kind of you're in thought.
You could argue that when you're more present, your ability to extract information from the information in your environment is higher.
Yeah. And
therefore you're more intelligent.
Well, and you have the awareness in terms of, yeah, exactly. So that was my comment for that.
Yes.
Thank you.
Daniel, right behind you, Gino.
Yeah, a couple of quick questions and an observation. First, if you look at the number of computations in theory that's done by a glass of water in about a second, it has more computations than all of the computers in all of history have been doing. It's on the order of something like 10 to the 30th calculations per second. So it's not surprising that you'd get 10 to the 11th computations per base pair for the transcriptor, and you can probably calculate it without black hole physics. You can do it with straight statistical mechanics. It's a back of an envelope calculation. The question I did have had to do with the decoherence time. The decoherence time you claim is awfully long. Is that a base pair or a that's in isolation or in
No,
solution?
that's dependent because the DNA is a long chain polymer, and these
Yeah.
are because the long polymer can have long relaxation times
Oh, so you're talking about the actual decoherence time of the whole strand.
of a DNA polymer.
But it has to be isolated. It's not going to be in solution.
No, this is in solution.
In solution, has a decoherence time that long?
Yeah,
Okay, that's surprising.
because I mean that's one of the key points in arguments
Well,
against quantum.
it's still surprising. I mean,
Say it again? You can have
decoherence time of
decoherence-free
a DNA strand
subspaces
shouldn't be that long, but you've done the calculation. I'm just surprised.
If you're
Interesting.
talking about the pi stack, which is all nonpolar aromatic down the center, that is could be a decoherence-free subspace isolated from the water.
So you can get decoherence-free subspaces in macromolecules that are quite long. And you can get long decoherence times in these
Well, the argument she's making, and I agree with, and I make the same argument, is that the aromatic pathways in a long, particularly helical molecule, is a decoherence-free substrate, protected by all the junk on the microtubule that Jack.
And I'm
just
not
said.
even explaining the mechanism. I'm just calculating it based on polymer physics. These are the relaxation times of DNA that can be very long.
That looked like Zurich's. Is that right?
This is not Zurich. Zurich has a definition for the decoherence time, but the relaxation time is from polymer physics.
Maybe we're talking about different things here.
Yeah.
I'm not sure.
Happy to talk afterwards. Yes.
One more question.
I'm curious if you had any thoughts about the transgenerational transmission of trauma epigenetics findings. Is this related at all to some of that work?
Could you say the question again?
The transgenerational transmission of trauma, some of that recent work in the psychological literature.
Transgenerational translation of trauma.
So we know about epigenetics, right? And information that's carried epigenetically. The question is, traditionally epigenetics is thought of in the context of transcription factors and molecular biology. And I guess the question this begs is, can information be stored in other physical ways that is being transmitted, both in the DNA sequence, but in the microenvironment of that DNA sequence, or in the generalized milieu or the environment, that information together determines what actually happens to that organism. For example, two twins can have the same DNA and the same oncogene that causes cancer, but one may get cancer and one may not. The difference is the environment. There's something in the environment playing the piano on that DNA that's determining who gets cancer and who doesn't. And so far we've been focusing just on the genetic sequence, but we really need to understand the interplay of how, and actually in our company we're building products to actually map not only the gene and gene expression, but tools to give people the power to understand how environmental influences modulate their gene expression patterns. And that's a little more.
Epigenetic memory in C. elegans, at least, is stored in the centriole. That's been shown. And somebody mentioned Lamarck today, who was the grandfather of epigenetics.
I mentioned Lamarck.
That was you?
Yes.
Well, thank you.
No, I was saying that at this DNA single molecule level, it could be that the molecular evolution could be not purely random, as Darwin would suggest, but influenced by the environment in a way that is more Lamarckian than Darwinian. Yes?
Here you go. You go.
If you say it's perhaps Lamarckian and influenced by the environment, could it also be influenced by the consciousness of its surroundings?
Yeah, so I mean, I think that as a field, the word consciousness needs to be very carefully defined, because we can all say the word consciousness and mean different things. Right. And so there's human consciousness, there's consciousness of a more generalized nature. So I think in order for me to properly answer that question, we should also agree on a definition of what consciousness is. But broadly speaking, that's the right idea.
Conferences have spent the entire time arguing about the definition and not getting to. Let's avoid that.
A quick one, actually no question, but reference to your implication. It is a delight to see your conclusion, your secondary one, about the scientific paradigm. It's a delight to see that on a screen in a conference such as this. So increasingly so, it's wonderful to see consciousness considered in the widest fashion. So thank you.
Yeah, actually, I want to make a point on that. If we look, I've been thinking about this very deeply for many years. If we look at this paradigm as opposed to this paradigm, so the old paradigm, let's call it the prevailing paradigm, is where matter attains a critical degree of complexity and then manifests consciousness, that goes with 20th century physics. But that also out of that comes several paradoxes and things we don't really understand about 20th century physics, and including Einstein's argument that quantum mechanics is somehow still incomplete in its description of reality. I would argue that in this paradigm, we can rederive the same laws of modern physics and it would be consistent with this paradigm. It's just that this paradigm would give us insights that we haven't thought of yet and perhaps help us reconcile some of these long-standing paradoxes that haven't moved too much in the last 100 years.
I think you're preaching to the choir on that one. Let's give Anita a great round of applause.